People. Uh, we started off in the previous class something about seepage forces, okay, and let's recap and spend a few minutes on this. In today's class, in fact, I intend to do a few problems. Jotted down 2 questions, and if we have time, we'll probably quickly go through the third question as well. So out of those 2 problems, they are based on seepage force, and just I would like to recap what we did the other day. We started with looking at soil permeability. We said permeability, there are semi-empirical equations for permeability, which depend upon the void ratio, the effective confining stress, and so on. In fact, the viscosity of the material or the flow or the fluid was also a parameter. If we moved on to seepage force, and we looked at the 3 sketches which are shown on this figure. The first one was no flow condition. In no flow condition, we looked at the stress distribution, and it was very similar to what we have been doing in the last few lectures. For flow downward and for the flow upward, remember we said upward flow, that is the last figure over here, the pore pressures increase. Okay, so just to make it easy for you to remember in advertisements for Complan or Bonvita, when children flex the muscles, they flex the muscles up to make it stronger. So upward flow would mean the pore water would increase. Okay, in fact, upward flow would cause the effective stress to decrease, the strength of the soil decreases. Downward flow causes the pore water pressure to decrease. Okay, so decrease in pore water pressure would cause an increase in effective stress. That is why the middle cartoon over here is effectively used for consolidating ground, for preparation of ground. This procedure is used. This procedure in fact is called as seepage induced consolidation. So if you do some Google search on seepage induced consolidation, you will probably get a number of examples on the second figure. We did a couple of examples on the last figure in which there was a case of soil liquefaction, and hopefully you would have gone home and did some background homework on this. In today's class, I'm going to close this and open up my problem sheet. Today is the 4th. Okay, yeah, just a second, right click, I know. Is that it? I know, I've been here for. So this problem sheet is lined up into number of pages. So please do not, I have right click so you can download it. Please do not scroll through the pages, just look at the first question that's over here. Okay, and I've been advised to zoom in. I'm not sure if you can zoom in. In any case, we're going to do it on paper, not to worry. Don't worry about this. This question, please go through it. We'll have zapped it on a sheet. So I'm going to show you on a sheet as well. Can you just go through this question? Zoom. Why don't you zoom in? Okay, they will zoom it from the end. We have to zoom, right? Yes, so we have to zoom. Okay, it's the same question which is on your if you can download. I've just zapped it on a sheet. Let me briefly explain what this question is about. Please do not start copying anything from the question. It will be there on your PC. Just understand what the question is about. It speaks about 2 cases. Okay, case 1 and case 2. Okay, in case 1, there are 2 soil layers, soil layer 1 and soil 2. They have different permeability. There is an overhead tank over the 2 layers. So there is an overhead tank with an overflow mechanism. So overflow means it keeps a constant water level at this level, and at the bottom somewhere over here again a constant water level is maintained. Without looking at any other thing, just there is a constant level there, constant level there. There is a head difference. Immediately on looking at this figure, it tells me that there would be a head loss. A head loss of, quickly if I look at it, if I want to calculate head loss between A and B, remember A is the topmost point of the soil, 1, B is the bottommost point, which is the exit point. If I need to look at the head loss, I just insert standpipe over here and standpipe over there and look at the level difference. Quickly, if I look at this figure, if I insert the standpipe over here, the water level in the standpipe will rise up to this level C, and if I insert a standpipe over here, the water level will not rise, it will just stay there. So in fact, the head difference or the head loss will be distance between C and D. Okay, just to put it in English, we are going to write all this thing in words, but the questions asked are, in both the cases, what is the flow? Okay, so if I want to look at flow, flow is Q. Remember, Q was flow, and we had an expression Q equals to Kia, K-I-A, Kia. So in fact, the first part of this question asks what is Q. Okay, Q for each of these two cases. The second part says the distribution of the total head. So it asks for stress distribution. So I apologize, total head distribution. We will look at this later. Let's look at the flow. Q equals to Kia, KIA. And for the case 1. So just to put it, we said in English, what is the head loss? Okay, case 1. Can you just zoom out? Yeah. Solution, let's call it 1. Case 1. Okay, case 1, I'm going to bring out this figure. This B, if I take as datum, okay, so remember the total head at B would be the sum of pressure head plus the elevation head. Okay, so total head at B. Pressure head plus the elevation head. Okay, let me bring back the figure. What's the pressure head at B? If I insert a standpipe, the height of water in this standpipe is the pressure head. So in fact, it is 0. And the second part, elevation head, I take this as datum, B as datum. So in fact, elevation head is also 0. So next, what is the total head at A? Okay, let me bring that the figure. That's the A level. The total head is the pressure head, meaning if I insert a standpipe over there, the water level in the standpipe would be this height, which is from 3 to 4.5, it's 1.5 meter. Okay, so pressure head plus the elevation head. Pressure head, we said, is the water level in the standpipe, it's 1.5 meter. What is the elevation head? Remember, the datum has to be the same for the problem. So datum was there at B. Elevation head is from here to there. The total distance is 1.5 plus 1.5. It's 3 meters. It gives me a total level of 4.5 meters. Okay. So head loss. No, I'll keep it there. So head loss, or the potential difference between A and B. Remember, it's just English, just to confuse people. It's in fact simple head loss, but we can also write as potential difference between A and B. So it's the difference between this value and the 0 value. So that equals to 4.5 minus 0, or 4.5 meters. Okay, so if I bring back the figure, we say water will flow from the top into the bottom second soil and come out. So the head loss, which we say is 4.5 meters, will be distributed between the two soils. Or can I just rephrase this statement? If water moves from soil 1 to soil 2, there would be some head loss in soil 1 and some head loss in soil 2. Both the head loss may not be the same. Definitely it may not be the same, because when water seeps through one, there would be some head loss, then seeps to second, there will be some second head loss. But there is one rider. What is the flow which comes out? Q, which comes out. Q definitely will be the same, because it is the same quantity of water which flows through first soil and the second soil. So Q, either I calculate Q from the first soil or the second soil, Q has to be the same. Okay, so let's look at this head loss thing. So I said this 4.5 meter is the head loss between soil 1 and soil 2. Yes. So can I just say this is the total head loss in soil 1 and soil 2. So if I say head loss in soil 1 is H1, remember H was the representation for head loss, and if H1 is the head loss in soil 1 and H2 in soil 2, so total head loss would be H1 plus H2. So just to put it in English, okay, let me just take a fresh piece of paper. Okay, we have a lot of paper to waste. So can I just say, in other words, if head loss in soil 1 is H1 and head loss in soil 2 is H2, then H1 plus H2 equals to 4.5. Okay, let me call this as equation 1. Okay, in this figure, back in this figure, we did say the Q is the same. Okay, Q is the same. So we have an expression for Q. Q equals to Kia. So can I say Q from soil 1 should be the same as Q from soil 2? Okay, so can I say Q equals to K1, that's the soil permeability of 1. Okay, I, so that's the hydraulic gradient of 1, and A, okay, equals to K2 I2A. Remember, A in both the cases are the same, because this is the area would mean this dimension times the dimension which comes out and hits you. Okay, so can I say area is the water flows through this times maybe a one unit dimension which comes out and hits you. So area in both the cases is the same. Okay, both the dimensions are the same. So can I say K1 I1 equals to K2 I2? What is the value of K1? K1 I1 equals to K2 I2. What is the value of K1? I think K1 in this figure is given as 1 into 10 to the power minus 3 meters per second, and K2 is given as 1 into 10 to the power minus 4 meter per second. So K1 I1, let me just open this up first. I have K1, I1 is H1, head loss in 1 over the length of first sample equals to K2 H2 over L2. Okay, I1 is head loss over the length over which the water travels, it's length 1. In both the cases, let me just bring back the figure, the length of water travel is the thickness of the soil layer, which is same 1.5 meter there and 1.5 meter here. In this example, the L1 and L2 equals 1.5 meter. So can I say K1, we say is 1 into 10 to the power minus 3 meters per second. H1 is unknown, okay, divided by L1, which is 1.5 meters. K2 equals to 1 into 10 to the power minus 4. H2 is unknown, and L2 is again 1.5, which gives me a relationship between H1 and H2 as H1 equals to 0.1 times H2. Let me call this as equation 2. Okay. Above we have looked at equation 1, which is sum of H1, H2. Second one, I have an expression between H1 and H2. If I solve for these equations 1 and 2, okay, you can go back home and try this. I have H2 equals to 4.09 meters and H1 equals to 0.41 meters. Okay, it's as simple as that. So if H1 and H2 are known, the question, let me just bring back the sheet. The question was flow. What is the flow? So in case 1, can I say flow equals to Q equals to KIA. So for because the flow from both the soils in this case is the same, so can I say Q? I can use soil 1 to calculate the flow. So K1, I1, A1, that equals to K1 is 10 to the power 1 into 10 to the power minus 3 meters per second. What is I1? Equals H1 by L1. We have just got H1 as 0.41. It travels through, water seeps through a length of 1.5 meters. And the third part is area A. What about area A? Let me just bring back the figure. It again, let me use the same logic. It flows through this area of this length times the 1 unit length which comes out and hits you. Okay, so can I say this length is 1.5 meter times the unit length which comes out and hits you. Okay, that should give you a value of 4.1 10 to the power minus 4 meter cube per second. Okay. I could have also deduced flow from the second soil. Q equals to K2 I2 A2. Okay. Remember we said the answer should be the same because the flow is the same. So if you would have plugged in the number, K2 is I think 1 into 10 to the power minus 4. I2 is H2 by L2. H2 is 4.09 and L2 is again 1.5 meter times the area, which is 1.5 times 1. If I plug in my numbers, I should get the same answer. Okay. Let me just pull down the question again. The question was quantity of flow in each case. So we have done flow for case 1. Also you are asked what is the distribution of total head with respect to elevation. Okay, I'm just going to quickly pull down a figure. And this, yeah, there's a lot of automation over here. I don't need to tell anyone. Things happen on their own. Okay, so this figure incidentally is on the same, is part of page 2 of the PDF document which you have just downloaded. Okay, it is there. Please do not draw. Just look at this figure carefully. I would like you to carefully draw this at home on a clean piece of graph paper. Okay, please look at this figure carefully. So horizontal axis I have taken as total head. Okay, nothing will stop you from taking this, plotting this in the vertical axis, but conveniently I have taken this as total head as starting from 0 going to 4.5 meter. The vertical axis I have taken as elevation. Obviously elevation is usually represented as vertical, but there's nothing stopping you from switching the two. So at A was the top of the soil layer, D was the bottom of soil layer 1 and top of soil layer 2. So it's the interface of the two soil. B was the bottommost point. So at the top of soil layer, the total head is 4.5 meter. Okay, so I've got a line over there. Okay, at the interface, I lost 0.41 meter. Okay, I lost where are you? I lost 0.41 meter at the H1. So from there to there, I lost 0.41. So remaining is 4.09. So that's the remaining head at this level. And at the bottommost point B, I have lost everything. So that's the 0 level over there. Okay, so I would like you to please go home and draw this on a clean piece of graph paper. It's just good practice, a simple problem, no rocket science. Okay. Let me switch on and go to our case 2. Oh, 10:21, so we still have time, a lot of time. Case 2 is the second figure over there. The two soil layers, soil 1 and 2, the same, which with same property as the previous one, meaning the soil permeability is the same. Soil 1 has 10 to the power minus 3 meter per second. Soil 2 has 10 to the power minus 4 meter per second. In this case, the flow occurs simultaneously through both the layers. Okay, so when the water exits, comes out at B, it's obvious that the water which comes out at B should be the sum of water which comes out from soil 1 and soil 2. Or can I say the total flow in this case should be flow through this one and flow through that one, or rephrase this statement, Q equals to Kia. Okay, so Q equals to this Q1 plus Q2. Okay, so flow in the previous case was the same, but in this case the flow is not the same. However, if I look at this carefully, if I insert the standpipe at A, standpipe at B, remember the elevation between the two water heads in the standpipe is the head loss. The head loss between A and B in this case, it's same. Obviously, because if I insert standpipe over here, water level shoots up to this level. If I insert a standpipe at B, let me draw this. If I insert a standpipe at A, water level shoots up to there. If I insert a standpipe at B, water level does not go anywhere, it stays there. So head loss is this whole thing. Okay, for both soil 1 and 2. Okay, so let's look at the case. Okay, case 2. So in case 2, just to put it in English, we are going to put the steps very just as same as the case 1. What I have is, so take elevation at B as datum. So B as datum. Therefore, total head at B equals to the elevation head plus the pressure head. I'm going to re-zap this figure. Total head at B equals to elevation head. B is date, so its elevation head is 0. And what about pressure head? Pressure head is also 0. So B equals to 0. What about total head at A? Let me bring back the figure. A equals to elevation head. Elevation head is this whole thing, which is 3 meters, plus the pressure head, which is this whole thing, which is 1.5 meter. So can I say total head at A is 3 plus 1.5 equals to 4.5 meter. Therefore, head loss equals to 4.5 minus 0, it's 4.5 meter. So we made a statement, since the flow occurs through both the soils simultaneously, the flow is not the same in soil 1 and soil 2, but the head loss is the same. So again, just to put it in English, we say, note, since flow occurs through both the soils simultaneously, 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 the head loss, that's H, okay, is the same. Okay, same in soil 1 and 2. Okay. However, total flow equals to flow in soil 1 plus flow in soil 2. Okay. Flow, we remember it's Q. We say Q equals to Kia. So that's the flow. So can I say flow in soil 1 is K1 I A plus K2 I A. I is the hydraulic gradient, okay, equals head loss over the distance over which the water will have to travel. If I zap this figure back, I is the head loss. We say head loss is the same over the distance over which the water has to travel. For both the soils, it is the same. So can I just bring back this again expression? So I for both the soils is the same. Okay, and incidentally the area is also the same. Okay, so can I say K1, remember it's 1 into 10 power minus 3, I equals to I, uh, did we calculate I? Oh, we forgot I. Let me just redo I over here. I equals to H by L. Okay, for both the soils, H is the head loss, which is 4.5 meters, and the distance over which the water has to travel, it is 3 meters. So 4.5 by 3 should give you a number which is 1.5. Okay, no units. So I is 1.5. Okay, we forgot to do it. Apologize. Let me bring back the sheet. So Q equals to K1. That's 1 into 10 to the power minus 3 times I, which is again 1.5. Okay, area. Let me just zap this figure again. The area is this length times the unit dimension which comes out and hits you. So this total thing is 1.5 meter. It's split into 2, 0.75 and 0.75. So area would be 0.75 times the unit length which comes out and hits you. So I have area as 0.75 times 1 plus K2. K2 is again, I think it's 1 into 10 power minus 4. I is the same. Area is incidentally is the same in this case. So if I plug in my numbers, I should get flow as 1.24 into 10 power minus 3 meter cube per second. Okay. Let me just zap this question again. Okay. The question was quantity of flow in each case. So we have just done for case 2. The second one was distribution of total head with respect to elevation. Okay. Let me bring back my total head picture. This case is the simplest of all. It's much simpler than the previous one. Remember, horizontal axis we labeled as the total head. Again, I would not like you to draw this figure. It is there on the PDF document which you have just downloaded. Please just concentrate on this figure, and if if possible, I would say I request that you go back home and draw it on a clean graph paper. So total head is goes up to 4.5 meters. At A, the total head was 4.5. That's the topmost of soil 1 and 2. And at the B, which is bottom, is 0. So it's just a straight line which joins A to B. Okay. Right. So let's move on to the next question. Okay, this question is there on the. You don't need to open up the computer. Okay, enough. Thank you. Okay, this is second question related to again flow. Okay. Please go through this question. Okay, what the question says is, there's a sand layer somewhere over there. You have a sand layer at the bottom, which is overlaid by a clay layer. Okay, clay layer. The thickness is given as 5 meter. There's a pond at the top of the clay layer. The question says, a standpipe has been inserted somewhere in the sand. Okay, it doesn't specify, just somewhere in the sand, and the water level in the standpipe rose up to 5 meters above the pond level. Okay, obviously there is the head. I must say total head in the sand layer is much higher than the head over there. That is why the water level rose much more than this level. So looking at this figure straight away, I should jump to conclusion that there is flow occurs upward. There is upward flow. If you look at the question carefully, the question also says the same thing. It says the same thing. Uh, Determine the quantity of flow into the pond in liters per day. Okay, we're not interested in this for the time being. It says what is the flow in the pond. So obviously it says what equals to Q, the small q. Small q equals to Kia, K-I-A. K is given to us because the water flows to this. So the next part is what is the I, hydraulic gradient. So that I think is the only challenge in the first part of this question. The second part says plot the vertical stress, effective, blah blah blah. But here it also says what is the horizontal stress distribution. We will not do this. It requires the knowledge of K naught. We don't have time to do this. I request that just ignore the last part. If I have to cancel this out, I would say ignore this part. Okay, but at the last part of this question there is a good point. It says there is no head loss in the sand layer. Okay, that's interesting. What it means is this standpipe, if I would have inserted at the bottom of the sand layer, middle, here, there, right up to the top of the sand layer, the water in the standpipe would ultimately rise up to the same level. So if I just want to draw a cartoon over here, the water level in the sand would be same here. Okay. Sorry about this line, but it just means this is the water level. Okay, so there is no head loss in the sand. That's what the last line means. Let's do this problem. Okay, so we did say because the level in the water in the standpipe rose above the pond level, so can I safely say Artesian's condition? Artesian conditions exist in the sand layer. In other words, the water in the standpipe, or sorry, water in the sand layer is under excess pressure. It just wants to blow out. Okay, that's what it means. So total head in sand. Okay, we're looking at head loss between the bottom of the head loss at this level and head loss between these two levels. Okay, we're looking at the head difference. Okay, the head loss between these two levels. So head loss over here would be the calculated as total head in sand first equals to the elevation head plus the pressure head. Okay, let me zap this figure again. I'm looking at this level. So elevation head, I can choose, in all previous problem we have taken elevation head, the datum as somewhere here, okay. I can choose the datum again as this level, but in this example the values have been given. So obviously the question suggests that I should choose this as datum, okay. There's no harm in choosing datum anywhere. So that is the datum for us. So let me just mark X, that is the datum. So if this is datum, the first part says elevation head. So I'm going below the datum. So this is 5 meters below, 10 meters below. So elevation head is minus 10 meters. Okay. Second part, pressure head. Pressure head would mean if I insert a standpipe over here, what is the level of water over which the standpipe goes? Obviously it has been given. Remember in this question, the position of the standpipe does not matter. There is no head loss in the sand layer. So it says it rose from here up to a level of plus 5. So I start counting from there. So there's a 5 meter over here plus another 5, 10 plus another 5, 15. So pressure head is 15. Okay. So sum is 5 meters. Okay. Second part, what is the total head at the clay surface? Okay, I have the same logic. Total head equals elevation head plus the pressure head. Okay, let me zap this figure again. Okay, it's too small. Let me zoom in now. It's too small. थोड़ा सा और bit come. Okay, stop. Yep. So you're looking at this clay layer, the top of clay layer. What is the elevation head? Remember this is datum, so you're 5 meters below. The elevation head is minus 5. What about the pressure head? Meaning if I insert a standpipe over here, the water level in the standpipe would be up to the pond level. Okay, so let me take a blue pen and draw a standpipe over here. The water level in the standpipe would be 5 meters. So if I have to do this total head, I get elevation head okay. There's a person next to me doing this magic. So elevation head is minus 5, pressure head is 5, okay, minus 5 below datum, 5 meters above, so total head is 0 meters. What about head loss? Is the difference between the two. So 5 minus 0, so I have 5 meters. Okay. Next part, hydraulic gradient. Come on, it's easy. Hydraulic gradient is head loss over the length over which the water has to travel equals 5 meters divided by the thickness of the clay layer, which is also 5. So get a hydraulic gradient of 1. Okay. Hydraulic gradient 1. Next part would be to calculate flow. Q equals to here. K of this clay layer is given. It's given as 1 into 10 power minus 7 meters per second. I we have just calculated is 1. Area. What's the area? Okay. Bring back this. Okay, it's a big pond. Okay, large pond. I can't calculate this area, so I have to take a unit area. So it's 1 length over here plus times the 1 unit length which comes out and hits you. So it's 1 square, let's call it square meter of area. Okay, so because the water flows upward. Okay, so it's 1 times 1 which comes out and hits you. So area I'm going to take as 1. So that gives me 1 into 10 power minus 7 meter cube per second. Hold on, the question says do not calculate in meter cube per second. It says calculate in liters per day. So you can plug in your number, convert meter cube to liters and second to days. You should have an answer which gives you 8.6 liters per day. Okay? You lose 8.6 liters per day in this condition. Okay? The same question says what is the stress distribution? Okay, this is the important part and I would like you to stay awake for the next 15 minutes. This is the most important part of this question. Plot the vertical stress in terms of total stress, pore water pressure and the effective stress. Okay, no need to zoom, please. I'm going to do this stress distribution. Okay, let me draw the small sketch over here. Okay, that was the top of the pond level. Somewhere over here was a clay layer and you had a sand layer. To draw in numbers, I think this was datum 0, this was minus 5, that's minus 10 and minus 20. We label this as A, let me call this as A, B, C and D. Okay, so we need what is the vertical stress distribution at A, B, C, D. Okay, let's take it at A. Okay, so total stress or total vertical stress, we call it as sigma. So I've just put suffix over there. Question says suffix V. In fact, it represents sigma V is the same thing as we have done before. We have been writing this as sigma, but in this question, the question, they have put it as sigma V, but it's the same thing. It's vertical stress for us. Total stress at A, there is no load. Okay, no load at the top is 0. What about pore pressure? U equals to 0. Therefore, the effective stress equals to 0. That's the difference between the two. Alright, so let's take at B. I would need this small sketch, so I'm going to fold this paper and keep this somewhere here so that it's always visible to me. So B is this point, okay, top of the clay layer. Total stress, sigma V. Okay, what about total stress? Is the anything above this level, the weight of anything above this level is total stress. This is the weight of water. So can I say equals to, it's 5 meters. So 5 gamma W. Okay, so I have in this question, I think gamma W, it has been given as take as 10 kilonewton per meter cube. So rather than 9.81, it suggests round it up to 10 kilonewton per meter cube. I'm going to take 5 times 10, that's 50 kilonewton per meter square. Okay, obviously 10 has been taken to simplify my life. I don't need a calculator. What about pore pressure? Okay, remember it's same as pore water pressure, but some engineers like to call it as pore pressure missing water. Obviously they don't deal with contaminated soil. Assume that everything is water. So what's pore pressure? Again, it's 5 meters of water. So can I say it's 5 times gamma W again? So it's again 50 kilonewton per meter square. Okay. Because at this level there is no, all head has been lost. Okay, starting from there, there was a additional head, 5 meters was the, was it 5 meters? Yes, it was 5 meters. So all the 5 meters has been lost from there to there. So there is no additional seepage head. So just to put it in English, There's no additional seepage pressure at B. That's B. All head has been lost at B. So I'm just only the pore pressure includes only the hydrostatic case, which is 50 kilonewton per meter square. So what about effective stress? Sigma V prime equals to sigma V minus pore water pressure. In this case, this is also 0. Okay? Obviously, effective stress at this level and this both the levels is 0. Next one at C. C is the bottom of the clay layer. Okay, so what about total stress? Let's start with sigma. The total stress is the weight of this water, so it's 5 times gamma W plus the weight of this soil. This soil is 5 meter thick, so 5 times gamma of clay, okay, that's equals to 5 into 10 plus 5 into what's the gamma of clay, please? You just bring it back. Gamma clay is given as 20 kilonewton per meter cube. I'm going to multiply this by 20. If you plug in your numbers, you should have an answer which is 150 kilonewton per meter square or kilopascal. Okay. This is the total stress. What about the pore pressure? Pore pressure at this level would be the hydrostatic. There has to be another component which is seepage pressure. So pore water pressure equals to 10 times gamma W. Okay, so it's 10, 5 meters over there, 5 meters over there. So it's 10. Just zoom out. Right. Plus the seepage pressure. Why I added this plus? Remember in the early part of this lecture we said if you eat a lot of Bonvita or Complan, you got to flex your muscle. Muscle flex means you know upward pressure, upward water flowing upward is positive. Okay? Remember this is positive because you eat a lot of Bonvita. You flex your muscle. Remember this is positive. Do not forget. So I get 10 times 10, which is over here, plus what is the seepage pressure? It should be the head, okay, the seepage head times the unit weight of water, so equals to 100 plus seepage head at this level is 5 meters, okay, all the 5 meters is lost in this soil, so at this level it is still 5 meters. Remember, if I have to calculate at any level in between, I just have to see what is the seepage pressure at that level. Okay, and in the previous class we said I times Z. I hope you have done this. Okay, but our problem is quite simple today. Seepage head is 5 meters of head, which still remains, times the unit weight of water, which is 10. That gives you 150 kilonewton per meter square. We have calculated at this level, but I repeat, if you had to calculate at any level, I would like you to go back home and review what was covered in the previous lecture. Okay. The pore water pressure is 150. What about effective vertical stress? Equals to 150 minus 150, which is again 0 kilonewton per meter square. Okay, that's C. What about D? In D, I have sigma V, which is the total vertical stress at D, this level, equals the weight of everything. 5 meters of water, 5 meters of this clay, 10 meters of this sand. So can I say 5 meters of water plus 5 meters of clay plus 10 meters of sand. Remember, these are all saturated, so I'm not writing brackets. I'm not writing saturated again. It's obviously it's below water table. This has to be saturated. So equals to 5 times 10 plus 5 times what's the unit weight of clay is given as 20 plus 10 times unit weight of sand is given as 18. Okay. Equals to 330 kilonewton per meter square. That's the total stress. What about the pore water pressure? Okay, please look at this carefully. Pore water pressure equals the hydrostatic head at this level. So it's the total weight of water at this level plus the seepage pressure. So 20 times gamma W. So 5 meters plus 5 meters plus 5 meters, 10 meters plus another 10 meters. So 20 meters times gamma W plus the seepage head times gamma W. Okay, so I have 20 times 10 plus what is the seepage head? Remember, if I bring back the figure, we said there is no head loss in this layer. It is assumed that there is no head loss in this sand. Obviously, for all practical purpose, this may be correct because major of the head loss only occurs in the clay layer. Okay, but in this example, all practical purpose, it says there is no head loss in the sand layer. So obviously, whatever was the seepage head at this level should be the same seepage head at the last level. So it's 5 meters times 10. Okay. I plug in my numbers, I should get 250 kilonewton per meter square. Okay. So what about my effective stress? Effective vertical stress equals to 330 total stress minus 250. It's 80 kilonewton per meter square. Okay. So you have total stress, pore water pressure, effective stress. Now I would like you to go back home and plot the stress distribution. Okay, we still have 5 minutes, 7 minutes in fact for any questions. But meanwhile, this is the stress distribution. I would like you to plot at home. So the first figure is the total stress, second is the pore water pressure, the third one is the effective stress. Again, please do not copy right now. It is part of the PDF document which you have just downloaded. Okay? If you have any questions, we can take up a question right now, or if you are happy with it, I can just simply, explain the third. Oh, sorry, missed it. I can quickly explain the last question. We have about 6 minutes remaining, and the best part of this today's class for me is there is no one waiting behind me. So obviously you may have a class at 11, or if it is just too much of write-up for today, let me know, we can wind up. Or else if you feel you're comfortable, we can at least explain what this last question is about. Any questions, please? No questions, right? Okay, I guess either everyone is happy about it. Okay, no questions. Okay, let me explain this figure, the last question. I'll just to quickly explain the last question, and give this an home assignment to you. The last question says there are 3 layers. So there are 3 layers, right? So K1, K2, K3 are the 3 layers. The soil permeability has been given. Okay, it says average hydraulic gradient of 0.3 in both horizontal and vertical flow. Okay, you are asked to find out what is the discharge. That's again Q, discharge velocity in each layer for horizontal flow. Okay, so horizontal flow you have to find out Q and the velocity. You are asked to find out what is the hydraulic gradient I and loss in head in each flow in each layer for vertical flow. Okay. Last is again plot this stress distribution. The first part of this question says discharge Q. If I have water which flows in the horizontal direction, okay, remember the water which comes out from the other end will be the sum of the water which comes out from this layer, and that layer. So obviously Q is equals Q1 plus Q2 plus Q3. It follows the same logic as the previous question. You can either do it this way or you can find out what is the average permeability in the horizontal direction given the 3 permeability. So the first one KH, I can find out KH from the 3 layers. If you remember the equation we had, KH was equal to K1H1 plus, okay, you can't see it, K2H2 plus K3H3 divided by H. Okay, that was the KH. I can find out what is the average permeability in the 3 directions. Okay, sorry, through the 3 soil. If KH is found out, I can then determine what is the flow using Q equals to KH, I and A. KH I have deduced from here, I is given as 0.3, A is the area. So it's the total area. So if I go back to the figure, I need to go back to the figure. The area would be this whole distance, that's 5 meters plus 2 meters plus 3 meters times the unit length which comes out and hits you. Okay, so that will give me the Q equals to Kia. So I can either use KH or I can use the same logic as we have done in the previous question. This will give me the discharge. Okay, discharge velocity, again, because discharge through all the 3 layers is not the same. So can I go back to this please? So Q equals to KIA. Remember Q is not the same in all the 3 layers. So I have Q equals to Q1 plus Q2 plus Q3. Okay, in this case I had used the average. Please do not mix up the two. Okay, if Q1, Q2, Q3 are different and I know Q equals to Kia, this equation gives me Q by A equals to Ki. Remember Q by A equals to Ki. I have just plugged in A from there. Or can I safely say this Q by A is my discharge velocity? Right? This discharge velocity will also not be the same if there is horizontal flow, because Q is not the same. Area is the area I have taken as per area of each soil layer. So the first part of this question, can I go back please? Discharge velocity I can deduce using the same equation which has been which was just shown on the piece of paper. You can do that. The last one again for vertical flow, if the flow occurs downward, I know my head loss through each apologize. If my flow is downward, I know my Q is the same. I can use the same logic and deduce the second part. Okay. I would like you to please go back home and try this. It's, it's very similar to what has been done. Okay. As I see it's 11 and I have no questions, I will wind up in the next 1 minute unless there is a question, please. Okay. No questions. Okay then, thank you. This closes the session, today's session. Next time we will do, I think if you look at the course content, next lecture is on stress distribution using theory of elasticity. So we'll spend an hour on it. Okay, thank you.